In this calculus video, we're going to be discussing the topic of linearization. Our objective for this video is to be able to use the method of linearization to approximate values for a function, f of x, near a specific x value, x equal a. So by the end of this lecture, you should be able to write the linearization for a function, and we call that L of x, near a given value, x equals a. You should be able to find an estimate for the value of the function at a value near x equals a using your linearization, which we call L of x. And you should also be able to decide if your estimate is an overestimate or an underestimate for f based on the concavity of the original function, f of x, at x equal a. All right, so this might sound complicated, but let's connect it to something we really know how to do. So here's something you've done a lot, and you're good at this, you know how to do this. So go ahead, write the equation of the line tangent to the given curve at x equals 0, and I'm going to give you the function f of x equals the square root of the quantity 1 plus x. So go ahead and press pause now, do that, and then we're going to connect it to our topic of linearization. So here's the solution you should have come up with. When you write the equation of the tangent line, you always need a point. So the first thing you should do is plug in 0, our x value, into f and figure out what the y value is. So we get our point. Here's our x sub 1 and our y sub 1. And then after you do that, you also need a slope. So we take the derivative, and we have to remember to use the power rule for this one. And when we rewrite it, we get this nice function. And when we figure out the value of the derivative at 0, which is going to be our slope, we get 1/2. So 1/2 is our slope. We go ahead and we plug our slope and our point into our point slope form. And remember, you're always going to use point slope form. Y minus y sub 1 equals m times the quantity x minus x sub 1. This is really the most useful form of a line in calculus. So make sure you have that memorized and make sure that's what you default to when you write the equation of a line. So here's the equation of our line. All right, so let's talk about what that means and how is linearization related to what we just did. Okay, so when we do linearization, what we're doing is we're finding the value, or we're writing the equation of a line at a point. So let's just draw a simple sketch, and let's look at what this means visually before we discuss it analytically. Let's call this f of x, and let's say I want the equation of this tangent line right here at this point, and let's call this x value, we'll call this x equals a. So this point right up here is going to be a, f of a. That's our x value and our y value. So this is our x sub 1 and this is our y sub 1. And what else do we need to write the equation of a line? I think we need a slope. So we have to figure out the slope of this tangent line. Well, the slope of the tangent line is the derivative of f. So our slope is going to be f prime at the given value a. Okay, so now we are going to grab these three things. We're going to grab our point, and we're going to grab our slope, and we're going to write the equation of our line. So the equation of our line is y minus y sub 1 equals m times the quantity x minus x sub 1. All right, so our y sub 1 is y minus f of a, the y value at x equals a equals m. Our slope is f prime at that x value, and we have x minus our x value, which is a. Okay, so if we write this in y equals form, we get y equals f of a, and I'm not going to distribute that, I'm just going to leave that the way it is, f prime of a times the quantity x minus a. What we have here, this is our linearization. So let me tell you what that means. What this equation does is it gives you a value y near this point x equals a. In other words, if I plugged in a plus 0.01 would be right here, you can see that very close to that x equals a point, kind of in this box, the line and the curve are almost the same. As we get further out, they kind of come apart, but the line is a really good estimator of the curve, okay? So I can use the line, which is much easier to plug points into a line and get out values than it is into something that's cubic. I can use this as an estimator. So the linearization is something you know how to do. It's writing the equation of a line at a given point, but instead of calling this y, we change this into L of x to indicate this is a line we're using to estimate the value of a function near a given point. So we just change that y into L of x, and we say L of x equals f of a plus f prime of a times the quantity x minus a, and we say this is a linearization near x equals a. And what we use this for? We use this to estimate the value of a function near a. So linearization is used to estimate the value of a function near x equals a. Now, the further you get away from your a value, the worse your estimate becomes. So, for example, if this is our a value, we would not want to use our line to estimate the value of the function here because the difference between the line and the function is quite great. So we want to stay very close to a when we use the linearization as an estimator. So let's go back to the example we originally looked at. What we did was we found the equation of the line tangent to the curve at x equals 0. So if I had asked you to find the linearization of f of x at x equals 0, what you're going to do is you're going to do exactly the same process. You're going to come up with this equation. So the equation that we found was y equals 1 plus 1/2 x. But now you're going to call this a linearization. So we're going to say this is a linearization for our function, and the equation of our line is 1 plus 1/2 x. But we need to say this is only good for values near x equals 0. So we're going to say at x equals 0. And this is called our center of approximation. So you always need to include your center of approximation when you're doing a linearization. Okay, so now we can do a few things with this. For example, if I say approximate the square root of 1.02. So this is what I want us to do. I want us to approximate the square root of 1.02. All right, so if you're trying to do this without a calculator, you know it's going to be pretty close to 1 because the square root of 1 is 1. But if we look at our function, if we know f of x equals the square root of 1 plus x, we could say that f of 0 would be the square root of 1 plus 0, and f of 0.02 would equal the square root of 1 plus 0.02, which is the square root of 1.02, which is exactly what we're looking for right here. So what I need to do is figure out how to do this, and we have a really good method to use to approximate this. So this is where I say, okay, I can't really do this in my head without a calculator, but I have a really good estimator right here, my linearization, which I'm going to use to estimate this value. So we're going to use linearization, and the x value we're going to use is 0.02. And if we plug this into our linearization, 1 plus 1/2 of 0.02, what we get is 1 plus 0.01, which is 1.01. So we would say that our function f of 0.02 is approximately the same as our linearization at 0.02, and we came up with 1.01. So we're going to say that the square root of 1.02 is approximately 1.01 using our linearization L of x. So this is a way that can be useful, and before calculators, this is how they had to do a lot of things like this. If you look up Wikipedia, you can see other uses for linearization. They're much more complex now.